Hello, friends. Good morning, good evening, and good afternoon, wherever you are in the world. Welcome again to my channel. Today, we are going to learn about the CAN protocol. If you want to pursue your career in the automotive industry, irrespective of the on-road vehicle or the off-road vehicle, you must learn the CAN protocol. It is not required to be an electronics engineer. If you are a mechanical engineer, computer engineer, you must know the CAN protocol because of its a low cost solution and the robustness. It is widely and practically used protocol in the vehicle. So today I will take you through the fundamentals of the CAN protocol. So after watching the video, you will definitely learn what is CAN, why it is used, what is the motivation behind, what is the history, why it is invented, what is the current trend, and what is the future for the CAN protocol. So let's start.
So let's start. Um, so I'm going to cover the CAN fundamentals, and definitely this would be very helpful for everyone. As I mentioned earlier, it is not required to have the basic understanding on the digital communication, but if you are the mechanical engineer or any other computer engineers or electronics engineers, after watching this video, you will definitely understand um, what is CAN protocol. So let's start. Um, So what is my plan today? What I'm going to cover? I'm going to cover what is the motivation behind the CAN protocol? What is history? What are the different advantages over the other network? Then what is CAN network? What is the role of CAN controller? Role of CAN transceiver? What is CAN bus? CAN structure? CAN frames? Then we'll touch base to the physical layer. What is physical layer? When we say the CAN communication network, what is physical layer? What are the different error states, how it is handled, how it is identified, how it is informed by the one issue to other issue, that we will touch base. Very important, bus load, how it bus load calculated, what happens the bus load goes higher than the range, what happens to the network, that's very important. And the next part is the J1 and 39 basics and the CAN FD. So J1 and 39 and the CAN FD is the extension. CAN FD is the current trend basically. So I would say if we will refer CAN protocol, then CAN FD is a feature for the CAN protocol. So we'll just touch base in the single slide or the two slide, what is CAN FD and what is J1 and 39 protocol. But our focus is from the motivation to the bus load calculation and all the terminologies being used in the CAN protocol. So if you see the image here, let me bring my pointer here. If you see the image, uh, let me bring the pointer. Okay, so if you see the left side figure in the conventional networking, in a vehicle, different ECUs communicate to the different ECUs. If the engine ECU wanted to send the torque information or the speed information to the transmission ECU, earlier the wired uh, sensors are used to sense that value and decode that value. And again, the wire is used to send that information from one ECU to the other ECU. So just if you imagine in the conventional networking, if this ECU wanted to send three signals information, it needs to have the three wire while sending the information to this ECU. When I refer the ECU, it's an electronics control unit, and it might be a AMT, it might be a engine EMS, it might be a EBS, or it might be a central body control unit, or it might be AMT, whatever the ECU are used in the vehicle that that represent the ECU. So just imagine if I wanted to send the 10 signal information or the 10 sensors information from one ECU to another ECU, definitely I need 10 wires in between the ECUs. So this is the conventional networking, and it was getting worst if you have or you need more sensor information to be transmitted from one ECU to another ECU. But when you jump to the next level, that is called the line networking or the bus networking, you see this issue tech participate into the communication. It sends and receives the information from this bus. And this is also sending and receiving the information using only two wires, or I would say the single wire. I won't say the single wire, but here we are just referring in the figure the single wire. So This is called the bus networking, and this is the conventional networking. That was the motivation for the invention of the CAN protocol, because here you need to have um more wiring harness, and it is very unreliable data or way of data transmission. So jumping to the next, what is the motivation? Yeah, automobiles are characterized by intensive electrification. Nowadays, all the ECUs are being electrified and they are sensing the information from the different sensors and transmitting from one ECU to other ECU. So electrification is increasing. When we look for the enhancement of the vehicle functionality, definitely um, we need to thought or we need to think about uh, the complexity as well. So intensive wiring efforts enabled limited data exchange. As you need more information to be transmitted from one issue to another issue, definitely we need more wiring harness, right? So as soon as you increase the intensive wiring harness, the data exchange get limited because of the complexity in the wiring harness. And because of the complexity, again, the next point covers that's the unreliable data transmission. And also there is no priority on the data transmission. If one issue want to send some information on highest priority and want to interrupt another issue, don't want to send that message if it is a low priority, that's not possible in the conventional communication, conventional method. And error handling also not possible. So all these points triggers the motivation, triggers the invention of this CAN protocol. And this is the history. When it started in 1980, Bosch started developing this CAN protocol. They officially released the first version 2.0A in 1986, and they officially released 2.0B in 1988. J1 and 3 was invented in 1993, and CAN is recently invented, and most of the vehicles, especially the European vehicles, start using this CAN protocol. So these are the advantages if we can compare the conventional networking and the CAN protocol based networking. These are the advantages. Prioritization of the messages. If I want to send a message with the highest priority, that's possible using the CAN protocol. How? We will definitely cover into the coming slides. Guarantee of the latency time. That is very important. If I'm expecting the periodicity of the CAN message is a 10 millisecond or the 100 millisecond, 1 millisecond, 5 millisecond, it should get delivered into the defined time frame. And that is achieved using this CAN protocol. Configuration complexity. It reduces the wiring harness efforts, right? Multicast the reception with the time synchronization. So here, there are multiple receivers which can receive the messages with the synchronized manner. Wide data consistency. You can send multiple data in a single frame. That's very important. So that's what system-wide data consistency. Multi-master. There is not a single master communication. If one of the issue fails, other issues transmit the messages as well as receives the messages from the network. So it is not kind of one master and the other slaves. If master fails, all network will stop. But here it is not the case. Every issue having the right to send the messages into the network as well as receive the messages into the network. That's what this is the beauty of the CAN protocol. It's a multi-master communication protocol. And as I mentioned earlier, if there are any error being found in the network, there should be a mechanism to detect that error or to take up from the network or warn that error. So that mechanism is possible using this CAN protocol. The signaling is very important as well as the detection is very important. Now, till now we have seen the motivation, history, and the advantages. So all these points definitely gives you the clarity why the CAN protocol is important. Now we are jumping into the technical details. What is CAN? When I say the CAN network, what are the different terminologies are being used? So let's start with that. So when I say the CAN communication, you should be very much clear on this image. You should have the CAN node, then the physical wire, two wires only, then the two termination resistance. One is at the one end and the other is the other end. The distance between these two end is called the main backbone length, and the length from one node to this main backbone is called the stub length basically. So this is a bus topology. in the bus way, it is connected. If this issue fails, it doesn't matter for this issue as well as for this issue. This cannot represent the issue in the vehicle. And one wire is called CAN high, one wire is called CAN low. So just to make a clear picture in your mind, when you say the CAN communication, you must be just imagine one more than one node and termination resistance and two wires. That's it. That's the CAN communication. But how it works? What has been compromised in this CAN node? What are the different parts of the CAN node? What is the value of this termination resistance? What is the length specified? Why this is main backbone stub length? Everything we will cover in the subsequent slides. So if you remember the earlier image, the CAN node, right? So there are number of CAN nodes, but practically there is a limitation. And that practical limitation is a subjective. If your one of the node is sending the multiple messages, more messages, and the one of the node is sending less messages, then that's fine. If all the issues, all the nodes sending more messages and making the traffic, more traffic into the bus, then there is a limitation on the CAN nodes. So number of CAN nodes are possible. You can put on 3, 4, 5, and in current vehicle, more than 20, 25 issues being connected over a CAN. It's a bus topology, very simple topology, main backbone, and this, on these stubs, you can connect the different issues. Physical transmission is a twisted two wires, only two wires, and it is a twisted pair. You have to twist it to avoid the signal reflection. I will cover that. What is the signal reflection or signal rejection in the coming slide. With the help of CAN protocol, you can send the data with the maximum data rate of 1 Mbps. We need to have this termination resistance at the end of the main backbone, and that is called the termination resistance, which are used to prevent the signal transient or the signal reflections or the uh, mirror effect of the signal. And so these are the important points that it uses this ISO 11898 architecture, which defines the node. And this node compromise this OSI layer, application, data link, and the physical layer. These three layers can be enough to cover the communication. So application and data link layer are the part of the your main controller and the CAN controller. And physical layer is the part of the trans receiver chip and the CAN bus. So let's see more into detail in the next slide how uh, basically these 7 layers are covered into the 3 layers only for the communication. So when we talk about the CAN controller, it is very important. When I say the one of the CAN node, that is the ECU. This is one issue, this is another issue, and this is again another issue. This host is your main microcontroller on your motherboard, on your ECU. CAN controller is another microcontroller, is another controller which communicate with your main microcontroller where your application code is written. And this CAN controller communicate with the CAN transceiver chip or the CAN transceiver. Basically, these two communicate each other. And once it gets the information from this physical link, it converts into the digital form and send it to the CAN controller. So very simple. On a CAN bus, basically there is a pulse, high, low, high, low, high, low. So some voltage levels are there, 3.5 volt, 1.5 volt, 3.5 volt, 1.5 volt. With the same time, um, with the periodicity of time, they fluctuate, right? So it sends the value, but it is in the physical form. To get that into the digital form, this CAN transceiver do that job. It converts that high voltage and the low voltage levels into 1 and 0 and push that to the CAN controller. But the smart work, the major work is done by the CAN controller. So CAN controller, what CAN controller do? It defines the baud rate, it prepares the CAN frame from that raw value, that 1010. It understands where the CAN frame is starting, where the CAN frame is stopping, what are the errors, what the baud rate is required. Everything is done inside the CAN controller. It's very important part. Earlier, in early 90s, or I would say 10 years back, um, This CAN controller and the CAN transceiver were the standalone chips. We need to um, use the separate kind of ICs, integrated circuits, on the motherboard for making your CAN network. But nowadays, it is a system on chip. It is a part of the main controller, whatever the main controller you are using for writing down your embedded code or the application code and flashing that code into this main controller memory. Inside this main controller only, this CAN controller and CAN transceivers are the part of that, and that is called um, a system on chip architecture. So this is very important, CAN controller. Now we have seen inside the CAN node, the host is there, CAN controller is there, CAN trans receiver is there. Then the physical wires are there, basically, which we can see by your open eyes. And this is inside the ECU. Okay, so what is the role of CAN controller? CAN controller defines the baud rate. You can program the baud rate. If you want the baud rate start from 125 kbps, or if you want 250 kbps, if you want 500 kbps, you can program it with the help of the baud rate prescaler, with the help of the oscillating frequency. You can define that. It's very easy. But whose role is this? CAN controllers role. You use bare registers, CAN controller registers you use. You cannot use main microcontroller register to define the baud rate. You use its registers. Then it handles the complete CAN protocol. When I say the complete CAN protocol, it make the frame from the start of bit to the end of frame. So it handles the transmission and reception of the messages. It defines the priority of the messages. It communicates between the application layer and the physical layer. As I said, the application layer is your main controller. The physical layer means you are the voltage level on your physical wires. So it communicates between them. It defines the error. So it handles the error. It defines the error states. TEC and REC are the transmit error counter. REC is the receive error counter. So based on the values resides in the TEC and REC, it defines the states of the error. It's very important. It defines the bus off state. If one of the ECU does not want to participate in the CAN communication, it goes to the bus off. But when it goes bus off, that has been defined by this CAN controller. It handles the synchronization, and it is nowadays, as I mentioned earlier, it is part of the system on chip. So moving to the next. So till now we have covered what are the different parts of the CAN network. When I say the CAN network, there is a main controller, your main application controller. Then there is a CAN controller. Then there is a CAN trans receiver. So let's see the CAN trans receiver. CAN trans receiver, basically it handles the physical bus connection. There are two pin bus pins which are called CAN high and CAN low, and it is characterized by very low electromagnetic emissions. It is very high noise immune, and it supports the high speed CAN trans receiver as well as the low speed CAN trans receiver. You can have the maximum data rate up to the 1 Mbps. Minimum data rate is also possible from 40 kbps to 125 kbps, but I am referring here 125 kbps as we are referring here to wide CAN communication. So low speed CAN trans receiver ensure the fault tolerant layout. This is the beauty of the when you are dealing with a low baud rate, that's a 40 kbps to 125 kbps. So till now we have covered the CAN trans receiver, CAN controller. CAN controller defines the baud rate, error handling, prepare the CAN frame. Everything is done by the CAN controller. CAN trans receiver take the 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 wide signal, that's the voltage levels, and convert into the digital frame, and it sent to the CAN control. That is the role of this CAN trans receiver. Now next we will see the last part of this CAN network is a CAN bus basically. So they are just two wires, differential signal transmission, which eliminates the negative effects of the interference voltages. It's two wire just twisted to each other to reduce the magnetic field, and it is increasing the data rate, and bus extension leads to signal reflection. So termination resistance prevents the reflection. So I will cover this part, how and what value are used as a termination resistance, and why 120 ohm only as a termination resistance, and why we need 60 ohm into the network. That I will cover in the coming slide. So this is how on the bus you can see the voltage levels high and low. So at the high you can see the 3.5 volt. If you just puncture the wire and you put the probes of the oscilloscope, you can see the high low waveform over there. CAN transducer takes this high low, that means 3.5 volt, 1.5 volt, this levels it takes and convert that into the 0101 and push that to the CAN controller. And then the role of the CAN controller is to take that data and understand what is the baud rate, what is the data end, where is the data field, where is the frame is ending. Everything is done by the CAN controller. And then it sends that CAN controller sends that entire frame to the main controller, your application controller. So very interesting part, the dominant bus level correspond to logical zero. Just remember, when I say the dominant bus levels means the priority. If the bus level is zero, that means it has a highest priority. If and the recessive bus level is correspond to logical one. Very simple. How the arbitration is handled, how the priority is handled by the physical layer is simply by this figure, very simply. And the answer to that is AND logic. If you see here, is AND logic is implemented. This is one issue. This is another issue. This is another issue. Inside that, there are two um, terminals. One is a sender, and other end it is also receiving, right? Because ECU is sending as well as receiving. Whatever he is sending, as well as sometime it needs some information, so it receives, and it is connected on the bus. So to understand this, just imagine there are three senders, one, two, three, and three senders are sending some information over a network and having some different identifiers. If the sender one identifier is this, I have converted into to the binary number, but just imagine this is the one identifier. This is the another identifier of the message, and this is the third identifier of the message sent by the sender one, sender two, and sender three respectively. So as I mentioned, wired and logic, if initially the sender one want to send the 0 bit onto the bus, that means here the 0 comes. It is a logical NOT is there. What will happen? The 1 will come and this transmitter will work as a closed switch. What will happen? It is pulled up to the high state. So this high state will get grounded. Because of this short, we are measuring or reading this R1 across this. So what I will get? I will get 0, right? So on bus, I'm getting 0. I'm sending 0. That means whatever the information I am sending, that is sent into the network. If the another sender is sending 0, so what will happen again? The 0 is there. So it will come here 1. This transistor will start flowing. That means it will act as a closed switch and you are just, so what will happen? Whatever the voltage will get grounded from this as well as from this as well, right? So, so what will happen? Here again, I would receive a 0. So I'm sending 0 and I'm receiving 0. That means it's okay. So this bit also getting sent to the network. For the third also the same thing will happen. So it is want to send 0 and it will read at their end. Yeah, I wanted to send 0 and on the bus also it is 0. That means I'm sending the right value. But just imagine for the next state, sender 1 wanted to send 1. So what will happen? I wanted to send 1. That means node 1 want to send 1. This will go 0. That means it will be open, right? Open means what I am doing, I'm reading the bus state. Okay. But what is the bus state? I'm sending 1. Let's check the bus state. Because of the next state, this sender sending the 0, right? The next bit is 0. This is a closed circuit. Because of this closed circuit, it is grounded. So I'm getting 0 here. So what will happen? The sender 1 will detect that I am sending 1, but on the bus I am getting 0. That means I will stop sending. I will not participate into the communication. This is how the arbitration work and the priority is defined. So if I decode this value is coming 0101. That means it is at 421. So this is 5, right? And again, some value, this is 5. So 55. And here, some value, this is some another value. So this is a logically higher numerical value compared to this. So that way, if you see into the CAN network, if one of the identifiers value is lesser than the others, then the lesser wins the arbitration. That's what it is written here. The dominant bus level correspond to the logical one. So it is a dominant. If the identifier has a logical numerical value low, it wins the race and it participates into the communication. And how? You just convert that identifier. Take the two example, take a 10 and take a 9. So definitely if you decode that into the binary and send one bit, one bit, you will understand that at one moment this 10 will stop and the 9 will start sending the messages. So this is very interesting how the CAN wins the arbitration and the priority has been set. So overall, how the CAN structure looks. Till now, we have covered the role of the CAN transceiver, how the CAN bus is there, physical layer is there, then CAN controller is there. This is how the structure. Inside the one node, that is inside the ECU, there is a microcontroller, main microcontroller, then CAN controller, CAN transceiver, and this is a physical wire, and this is a physical termination register. That's the 120 ohm. So I guess till now the CAN structure is clear. Now again we will go more into detail about the CAN frames and everything. Before jumping to the next slide or the next section of this training, let's jump to the basic questionnaires. The first question, which component of the CAN node handles the CAN protocol? Who handles the CAN protocol in a CAN node? As I mentioned, in a CAN node, three parts are there: the main microcontroller, CAN controller, CAN transceiver. CAN transceiver receiver are connected to the bus. It just take the physical value and convert that into the 010 and push to the CAN controller. Main microcontroller do the main task of the application layer. So who handle the CAN protocol? The answer is CAN controller. The next question is, low speed CAN transistor is characterized by the following properties. The answer is error tolerance. I have covered this in the previous slide. You just go back to the video, you will understand what is the error tolerance. Reflection in the high speed CAN network are avoided by termination of the bus end. Yes, it is. Yes, because of the this signal reflections, this is the fundamentals of the transmission line. You cannot keep the transmission line open at the other end. If you are keeping that open at the other end, and if you are sending some voltage or some signals at the beginning of the transmission line, and if you are expecting the same voltage level at the end of the transmission line, you will never get the same level. The signal gets deteriorates because of the noise and the reflections and everything. So there must be a termination over there to avoid the signal reflections. The next is logic 0 correspond to the receives bus level. No, logic 0 is a dominant state. CAN network has the following underlying architecture. What is the architecture being used in the CAN network? That is the beauty. And this the answer is multi-master line topology. There is no slave or multi-master slave communication. It's a multi-master. Everyone can participate. And it's not a ring topology. In the ring topology, if one of the issue fails, the link breaks between the other issue and the communication stops. Next question is termination resistance of the CAN bus is. There are two answers, but at the moment I would say the 120 ohm from both end is the right answer. And sometimes if the less issues or the number of nodes are less into the CAN communication, the length between the main backbone, the stub length are lesser, then even you can use a single 60 ohm from a single end. That also works. But here, let's talk very practical and robust scenario. So 120 ohm from the both end. That means the resultant the termination resistance value is 60 ohm into the bus network. Keep in mind that when you go to the vehicle and look for the termination resistance, always switch off the power of the vehicle. Do not switch on the ignition, or even do not put on the battery connected to the ECU. Keep everything off. Make sure that the ECU is not getting power. Then use your multimeter, turn the multimeter tab on the resistance, and just puncture the CAN-H canal and check the resistance. Ideally, it should be a 60 ohm, but practically you can get the value of 50 ohm, ranging from 50 ohm or even 57 ohm to the 61 or 62 ohm. If that is the value, that means your network is perfect. There is no any error in the physical network. If some another value coming there or 40 or something, that means there are multiple 120 ohm or the three 120 ohm termination resistance are into the network, as three getting parallel, the resultant value getting accordingly over there. So make sure that you will get the 60 ohm. That means practically 57, 56 or 61, 62 is good enough. So this is the basic. We have covered the basic with the basic questionnaire, and now we are ready for the next level. In the next level, we will jump into the detail of the CAN frames. When I say CAN is used to carry some information, so how it carries the information? For that, we need a CAN frame. So what is CAN frame? And what are the different types of the CAN frame? So there are four types of basically four types of the CAN frames are there. Data frame, which carries the data from one transmitter to the other. That means transmitter to receiver, and it's a multi-master. So every ECU has a data frame. If he wants to send, or it wants to send the information to the network, it must have the data frame. The remote frame, very interesting. Suppose I don't want to send the information to any of the ECU, but I want to get some information, right? So that is called a remote frame, transmitted by the bus unit to request the transmission of the data frame with the same identifier. That means if I send some remote frame with the identifier of 100, the ECUs connected into the network understand that I wanted to get the information uh, of the CAN frame with identified 100, and which issue, whatever the issue having that information, it sends that information into the network. So this is a request-based communication. So in the remote frame, there is no any data field, only identifier is required. You just send at once into the network. At the other end, the other issue they understand that this much of the identifier information is requested by one of the ECU into the network, and I need to send that information. So request-based communication happens with the help of this remote frame. Next is error frame, transmitted by any of the unit. If someone is detecting while receiving the CAN messages, if errors are there, then it sends the error frame. If during the transmission some error occurs, it sends the transmit error. So that way the error handling happens. Overload frame used to provide the extra delay between the two frames. So this is what preceding and the succeeding data, or the remote frames. If I'm consecutively sending two frames, there should be some distance or some time in between these two frames, and that has been carried out by this overload frame. So let's see the data frame. What are the different fields are there and how the data frame looks like. Okay, so this is a data frame. If you see the data frame here, there are the different fields. This is the start of frame field, arbitration field, control field, data field, CRC field. And start of frame bit is always 0. Arbitration field is, as I mentioned earlier, it contains the identifier, and based on the identifier and the logical ANDing operations, it defines which identifier of the which meshes get highest priority into the network. If more than two ECUs wanted to send the messages into the network at the same time, that is called the arbitration, basically. If at the same time there is no race between the two ECU or the two messages, then there is no need to do this priority. But at the same time, as it is a multi-master. I wanted to send some message, or some another EC wanted to send the message. So it should not happen at the same time. If we at the same time, then there is arbitration comes. Okay. But when I say the arbitration, what are the what is inside the arbitration field basically? So inside the arbitration field, there is um, there is a identifier field basically. If your frame is 11 bit, it's a standard frame, then there are 11 bits are reserved over there. Then there is one another bit is reserved, that is called RTR bit. I will cover that into the next slide. So RTR is a remote transmission request. So this is been covered into the arbitration field. So let's jump to the next slide here. Okay, so this is arbitration field where identifier and RTR. If I wanted to send or I wanted to request some message, then if I wanted to send the remote frame, then this bit will get set to 1. If my CAN frame is standard, then it's 11-bit identifier. 11 bits are reserved here. And the next field is a control field. Control field contains the DLC and this ID, and the reserve bit is there. ID is used for the extended data frame basically, and DLC is a data length code. So if you are working on the application side, you are capturing the data on the vehicle, decoding that data. You don't need to worry about all these fields. You only interested in the identifier. You are even not interested in the startup frame. You are not interested in the CRC, delimiter, acknowledgement, nothing. You only interested in the DLC, identifier, and the data field. And more, if you wanted to do the data analysis on that, then you are more interested in the data field only and the identifier. That's it. Not even require the DLC field. DLC field is a data length code which define it's a 4-bit result for the 4-bit. If I say 000, that means there is no data available, 0 bytes of information available. This field is a 8-byte field. Then the CRC sequence is a 16-bit field. 15-bit is for the delimiter. 15-bit is for cyclic redundancy check calculation for handling the error. 1 is for the delimiter. This is delimiter. So this is 15 and 1 is a 16-bit. This is the acknowledgement field. Acknowledgement field is only 2-bit field, and the last acknowledgement, this is 1 and this is a delimiter, and the last one is end of frame. It's a 7-bit field basically. So it starts from here. When the 0 comes, they should understand that the next 11 bit is my identifier. So it takes that 11 bits and decode that. Whose job is this? CAN controller job is this to understand that. The next it understand RTR is 0. That means this is a data frame. Then I have to leave this 2 bits. If it is 0, that means no any extended identifier there. So and this is reserved. So DLC. Then again it will look for the 4. If it is a 0001 or 1000, that means it is 8. So 8 byte of information is available. So I will take into account only the 8 fields. If it is a 6, that means I will take into account of 6 fields only. That way you can reduce the size of the frame. As you reduce the size of the frame, the bus load also reduces. That is very important. You are sending less number of bits into the network. So this is for the standard frame. And if we go for the extended frame, there are few more fields are added here. How it is identified? The 11-bit base identifier is here. Substitute remote request. This RTR is replaced by the substitute remote request. This bit is read as a remote request, a substitute remote request, and this ID is extended. Here you see this is a 0, this is 1 here. So that means it is an extended identifier, and the extended identifier is a 29-bit identifier in a CAN network. What is mean by extended and standard? Standard means 11-bit. You can use the 11-bit to define the number for any specific message. So 2 raised to 11 are the number of messages you can send. Ideally, but practically there is a limitation. But ideally, theoretically, we can say if I'm using standard CAN communication, I can send 2 raised to 11 messages. So 0 identifier up to the 2 raised to 11, whatever the maximum value, it will get decoded. Okay, and when I say the 29-bit, that means 2 raised to 29 messages I can send into the network. So number of messages increases here, but keep in mind that your frame size also increases. Next field, this is 11, and then the remaining 18 are the extended identifier. And the RTR, these are the reserved here, and the DLC is again used for the data field. So if you decode this value from the bits, and if it is 8, that means we have to count the next 8 bytes. This is 8-byte field. 8 bytes are the data field. Then the CRC sequence delimiter, CRC delimiter, acknowledgement field are the common, and the end of field is common in even in standard CAN, extended CAN, as well as in the J1 and 3.9 as well. So this is very common. Okay. So moving to the next, so till now we have covered very important, that is the CAN frame. So let's jump to the um, next, that is the remote frame. So I have earlier explained that the remote frame is basically if some ECU wanted to request some information, so it only send the identifier. Here you see the identifier field is there. RTR is 1, earlier it was 0. These are the result and the DLC. Here definitely it should be 0, but if you set something over there and this is 1, it don't care. It don't care. The data field is not there. Data field is 0. It decoding that the next bits are as a CRC sequence. So it calculates the cyclic redundancy check for the error handling and all. So this is how the remote frame works. The request-based communication. Moving to the next is a CRC. So this is frame acknowledgement. I guess this is also I have covered that acknowledgement slot and acknowledgement delimiter is there. So jumping into the more detail about this acknowledgement. So every node receiving an accurate message overwrites this recessive bits in the original message with the dominant bit. So it is indicating basically an error-free message has been sent. So should a receiving node detect an error and leave this bit recessive, it discards the message, and sending nodes repeats the message after re-arbitration. So in this way, each node acknowledge the integrity of its data. Acknowledge field is 2 bits. Now one is for the acknowledge bit and the second is for the delimiter. So this is how the acknowledge frame is being used basically. So next one is jumping to the next slide. Is a bit stuffing. So what is bit stuffing and why it is required? Suppose I want to send some information. I am as a node, I am as an ECU, want to send some information. But if I am continuously sending logical high state or the logical 0 state instead of changing the information, continuously zeros or continuously ones are going on the bus, definitely either the wire is shorted, high CAN bus is shorted towards the VCC or towards the ground, or something is wrong, right? There should be some change in the information or signal change should happen over there. To detect that, the bit stepping mechanism is used in the CAN network. So every transmitter, when it sends the information, it stuffs the 6th bit as inverted if it detects the 5 consecutive bits are there. So in very simple, if sender is sending, first bit is 0, second bit is 0, third bit is 0, fourth, fifth, 5 bits are continuously 0. That means it will stop a bit such a way that it will invert the logic state of the earlier. If it is logically 0, it goes for the logical high. If it is logical high, see here, if it is logical high, then it stops the logical 0. So this is the way the bit stuffing happens to understand or to decode either there is no any error into the network, or this is how the bit stuffing is required. The time for the question. Okay, so summarizing what we have learned earlier, we have gone through the different fields of the data frames. What are the different data frames? What are the different frames? Data frame, remote frame. Then we have seen overload frame, and as well as we have seen the different fields of like identifier field, DLC, data field, CRC, acknowledgement, end of frame, that way. So let's jump to the questions. Which of these message type are described in the CAN protocol? The answer is we have described the remote frame, data frame, and yeah, we have talked about this event triggered frame uh, that is remote request frame basically. So next question is, which of these fields are not part of the data frame? Data field, yeah, it is a part of data frame. Identifier, yes. Remote transmission request, yes. Synchronization break, it is not a part of the data frame. So answer is 3. Which of the data frame fields serves the difference between the data frame and the remote frame? The answer is very simple. Remote transmission request bit, right? If it is 1, that means it's a remote frame. It is 0, that means a data frame. Match up the field of the data frame with the correct bit counts. So you can study it later, but I'll answer here. The standard frame goes up to the 60, I guess 64 bytes. So, oh, sorry, it's an identifier. So standard identifier is a 11 bit. Data length code DLC is a 6 bit, 4 bit for DLC. And oh, it's a 4 bit then. Yeah. Extended identifier is a 29 bit. Acknowledgement field. What is the answer? Acknowledgement only 2 bit. One is for acknowledgement integrity and the another for acknowledgement delimiter. Control field, yes, the control field covers this DLC and 2 reserve bits. So it's a 6 bit basically. 4 for DLC and 2 for the reserved. The CRC field is a cyclic redundancy field. What is the length? Length is 16 bits. The answer is 16 bit. 15 bit is for cyclic redundancy check calculation and 1 is for the delimiter. Moving to the next question, which of the field of the data or remote frame does the cyclic redundancy check protect? The answer is CRC field. Let us assume that the all receivers acknowledge transmission of the data frame negatively. Which of the following error does the sender detect? If it is continuously negatively, then that means there is, what is the error? That is the stuffing error there. Right. Moving to the next. So-called the data frame is used for the data transmission in the CAN network. What is the maximum number of data bits that can be transmitted with the data frame? Not of bits, basically. In the data frame, what is the maximum number of data bits? It's a 64. The reason is 8 byte information you can send. So 8 into 8, 1 byte is 8 bits. So 64 bits you can send, right? Is it true that the identifier of the data or the remote frame addresses a specific CAN node? Yes, it's true. Identifier of the data or the remote frame addresses a specific CAN node. Yep. The CAN protocol specifies that the receiver acknowledges is data in the remote frame. Is it true that the acknowledgement is made after the transmission of the data or the remote frame? Yes. The acknowledgement is made only after the transmission of the data. So yeah, so till now we started with the CAN structure. What are the different terminologies used? What are the different parts of the CAN bus? Starting from the CAN controller, CAN transceiver, then the CAN bus, then we jump to the data frames, then remote frame, error frame, and then now we are jumping to the next level, that is the physical layer. Physical layer means you can visualize, you can see by your open eyes the two wire, that's the twisted pair wires. So as I mentioned here, in the vehicle, let's say this is a EMS, is AMT, this is CBCU, and this is any another ECU, this battery ECU, or is a traction motor controller, or this is the battery, let's say BMS, battery model system, or a battery controller. So the termination resistance are always kept or put into the ECU or next to the ECU, which are making the longest distance into the CAN. If this ECU and this ECU are at the longest distance, that means there should be 120 ohm resistance. And this is the theory of the transmission line. Basically, you need to put down the termination resistance there where you are getting the maximum distance between the two ECUs, and that is called the main backbone. And whatever the ECUs are connected in this main backbone is called the stub length basically. So termination resistance are 120 ohm to avoid the signal reflection, and maximum stub length is 1 meter to 3 meters. You can go up to 1 meter to 3 meter, and this main backbone you can go up to the 40 meters. This is the theory says. Yep. So, but again, the question is why this 120 ohm termination? Why not any other termination or any higher values? Very simple. This is the fundamentals of the transmission line. As I mentioned earlier, if you are sending some voltage or some pulse with some voltage level at the beginning of the transmission line, and if you are measuring at the other end of the transmission line where that transmission lines are open, you will never get the same voltage level at the other end. Never ever. So in CAN, it's the type of CAN bus is intended to implement by a twisted pair of wires. There are different transmission lines. Coaxial cable is there, then um, different wires are there, right? A coaxial, twisted pair, single wire, only two wires. That way, the transmission communication happens. So in the CAN commission, it's a twisted pair wire. The termination in this, the transmission line impedance of the unspecified twisted pair is not exact. Why we need a 120 ohm termination resistance? The reason is we need to look for the characteristics impedance of the transmission line. And it is practically observed that for the coaxial, termination resistance value is of 50 to 75 ohm only, not more than that. It's very common. It's common for the coaxial termination. And for the Cat5 transmission line, it's 100 ohm. For the CAN and RS485, it's 120, not more than 120. It is even identified that the 100 ohm is a characteristic impedance. But to put a right figure at the robust value, it is identified that the 120 ohm is going to be close most of the time for the relatively large wires commonly used in the CAN protocol. That's why when it comes to the CAN and RS485, the specification is officially 120 ohm. But unless you are going to a higher baud rate, the difference is small enough that you cannot use Cat5 for the CAN with a 120 ohm termination resistance. So hope it is clear now why we are using the termination resistance of 120 ohm. This is because when we consider the main backbone length of 40 meter, the stub length of 3 meter, and if we calculate the characteristic impedance, what is the characteristic impedance? It's the inductance and capacitance present into the line, right? If you calculate that, you would not get the value more than 120 ohm. It's a worst case value. So that's what the 120 ohm termination is universally accepted in the CAN protocol. So let's jump to the next slide. So what is the different error states? Till now we have discussed that CAN controller handles defining the baud rate, bus off, errors and everything. But what is different error states are handled by the CAN controller. So that error states are error active state, warning limit state, error passive, and the last state is a bus off state. If your transmitter error counter and receive error counter, there are two counters inside all CAN controller. What happens as soon as it detects the error during the transmission or during the receiving the messages, it start increasing their counter respectively. If during transmission, TC start increasing, right? If it is less than 95, you are in the error active state. There is no need to take any action from the ECU, right? Who is detecting that error? When the value for this counter TEC and REC goes greater than 96 or equal to the 96, then it enters into the warning limit. If you use the different CAN tools like Interpret CS or Vector Canalizer, you can see these values and even you can see the warning limit. So those who are working on the application side, developing the codes for specific application, the main microcontroller, they need to monitor this TEC and REC from the CAN controller and take the action accordingly. This is a warning that I'm going to enter into the error. I'm just warning you, please take a proper action. Okay. So error passive. When it enters the error passive, when the REC and TEC are greater than or equal to the 128. And if the TEC are greater than or equal to 256, then it goes to the bus off state. What is bus off state? Bus off state is basically ECU stop participating into the CAN communication. Does not even transmit the messages or not even receive the messages. It completely stop the communication into the network. To avoid that, as soon as your transmit error counter and receive error counter goes more than 96 or enter into the warning limit, the application developer or program needs to take care about the errors, has to clear the error or stop connection, send some messages, take the action that way. It is purely dependent on the application. So, but what is the role of bus load? When I say the bus load, what is bus load basically? And it's very simple how to calculate the bus load also. It is purely dependent the number of message, baud rate, your oscillating frequency, and everything it matters, the standard frame, the CAN frame. So I'll take you through the one example so that you would easily understand how to calculate the bus load as well. So when the number of nodes want to transmit the message in a short time on the bus, then the bus load increases. Increased bus load leads to the bus off state, and the bus off means the node or the ECO, one of the node will stop sending or even participating into the CAN communication. This is not good sign, right? So where it is, what are the different factors on which it is depending on? It is depending on the number of bits composed into the frame. It's a standard frame, it is an extended frame. It matters. Periodicity of the message. This is very important. If I am sending the message with the highest periodicity, when I say the highest periodicity, that means 5 milliseconds, 1 millisecond is the highest periodicity. And if the another message is 100 millisecond or 1000 millisecond, that means 1 second, then there is a low periodicity of the message. If the highest periodicity, that means 5 compared to the 100 and 1000, bus load increases. The baud rate, on which baud rate you are communicating. CAN supports 125 kbps to 1 mbps. If you are at the higher end, again the bus load increases. Yeah. So looking at the practical examples, all the vehicle manufacturer, all the tier one suppliers in the commercial vehicle have accepted that the CAN bus load should not be higher than the 70%. In the passenger car, it should not be greater than the 20 to 30%. This is a bit subjective. Sometimes it may vary. In some cases, it can go up to 80, 90, but it is purely dependent how the CAN network defined where the agreements and terms and conditions agreed by the different supplier. This is the general statement here. The commercial vehicle, generally 70% is a bus load accepted. For the passenger cars, up to the maximum up to the 30% CAN bus load is accepted. Okay, so it is clear now what is bus load and what are the different factors it is required. So let's calculate the bus load. As I mentioned here, the number of bits, then the periodicity of the message, and the baud rate. These three factors are required to calculate the bus load. We'll take the one example. I'll take it to the one example. Let's assume that you are dealing with a standard data frame. So in the standard data frame, including all the data fields, 8 byte of information, the size of the frame comes is a 125 bits. Assume that you are working on the 500 kbps. So if I calculate the bit time, 500 kbps means if I calculate the bit time and convert into this, so I'll get 2 microsecond of the bit time. It's a kbps, right? So this is how it is converted. And I'm getting here, the 2 microsecond is a bit time. In first step is you must know the size of your frame. Then you must know the baud rate where we are dealing with. Then the next one is to calculate the one frame time to transfer to complete one frame. Okay, this is for one bit, right? If I'm considering the 125 bits are there, right? Then I need 250. Definitely it will get multiplied with this factor. So you will get 250 microsecond time to send one frame of a standard data frame with a baud rate of 500 kbps in a network. So assume that you are expecting your message periodicity is 100 millisecond. Okay, so this means that for 100 millisecond, the bus will be occupied only for 250 microsecond, right? So what is the utilization of the bus? Out of 100 millisecond, the bus is utilized to send this frame on this baud rate and this frame size 250 out of 100 milliseconds. So bus speed is only 0.25, right? So this is how the calculation is done. So, but here I'm just assuming that the one message, as your messages goes on increasing, this number also goes on increasing. If you look for the vehicle log, there would be 100, 200 can messages. The baud rate may change, the frame size may change, the periodicity may change for the different message. And this should not go higher than the 70, generally not 70% in commercial vehicle and 30% in the passenger car. So this is what I have covered everything for the CAN protocol, starting from the CAN structure, different terminologies like CAN controller, CAN bus, CAN transceiver, main microcontroller, that is a CAN node. Then termination resistance. Why we need 120 termination resistance? What is CAN frame? What is acknowledgement field? What is data field? Acknowledgement field in CRC calculations, delimiter, end of frame, data field, DLC, everything we have covered. And we touched base to different questionnaires as well as what is the use of this bus load and how we can calculate that, right? So this is how the CAN is covered. If you have any question, please feel free to drop your questions into the comment. So let's jump and quickly look for the J1939 and the CAN ABD. As I mentioned, my focus is on the CAN protocol, but J1939 is an extension of the CAN protocol. So let's also look for this J1939 protocol. So this is developed by SAE, Society of Automotive Engineers, and specifically for heavy duty vehicles. Heavy duty vehicle, that is a commercial vehicle. So J1N protocol are used in the commercial vehicle, and this normal CAN, that's a CAN 2A, 2B, is being used for passenger cars. It is a higher layer protocol based on the controller area network. That's the CAN protocol. Most of the time for the J1N39 in the automotive application, I'm specifically highlighting the automotive application. On-road vehicles, baud rate is 250 kbps is fixed. But on the off-road vehicle, there is a flexibility. You can change the baud rate, though it is on the J1939. It is kind of extended CAN. Okay, but the field where we define the IDE, RTR, the extended data identifier, and the standard data identifier, base identifier, it's a bit different than the extended CAN frame and this J1N3 frame. So let's see in the next slide what is J1N3 message format. So it's transferred. This can be used to send again 2 raised to 29 are the number of messages you can send. But the beauty of this J1N39 is you can send up to 1785 data bytes in a single frame. Only you can send the 8 bytes, but with the help of transport protocol using TPCM and TPDT, that's a transmission protocol communication management and transmission protocol connection data. TPCM connection management and TPDT data transmission. Okay, you can send up to the 1785. So it tells you the number of frames. Initially, you send one frame. In the subsequently, it's still the second frame. The data is connected to the first frame. So that way you can send more data with the help of this J1N39, and you can send 1785 bytes of data. So the very important point is that the PGN, that the parameter group number, this is manufacturer specific. The source address also universally accepted. For the engine, normally it has been accepted that 00 is the source address. For the transmission, it is 03. For the central body control unit, it's a 21. For the braking system, it's a 0B. That way it is universally accepted. And it includes the diagnostic feature as well. This is how the frame looks like. Again, the start of frame. As I earlier mentioned that the CRC field Acknowledge field and this end of frame field are common in all the frames, including RTR, a remote frame, data frame, as well as this standard frame and extended frame, as well as J1 and 3. Only differences, major differences here basically. So the 29-bit field is basically used as a CAN identifier in the J1 and 300. So it's a identifier, but it consists of three fields. One is three bits are reserved for is are for the priority, which defines the priority of the message. The next one is a pigeon, and the last is a source address. As I mentioned, 00. That means 0000 means engine message. If it is 0000 oh sorry 000 that means it is a transmission. So it is universally accepted. So the last one byte tells you in this 29-bit tells you the source address, who is sending that message. And this 18-bit is a pigeon that is called a parameter group number. It's very interesting. It consists of four fields. These are reserved. This data page is used for the extension. If you want more data to be sent, you set this one. If you want to send less identifier, less messages, then you set this 0. Okay, so this is for the future use. This is very interesting. If the PDO format value, the value inside this 8-bit is lesser than 240, if it is a 0 to 239, that means whatever the value resides in this field, that is a PDO specific, is a destination address. Suppose here the value is, let's say 02, or let's say 10 or 20 something. That means this is lesser than 239. And here is the value is, let's say 0B. That means this entire frame is a specific, destination specific. And what is the destination is 0B. It's a brake system. So that way you can make the J1N39 frame as a destination specific frame. There are a lot many uses for the J1N39 protocol. Different standards are there, J1N39 standards based on the SE. New releases have happened from the 1994. First release was happened in the 1994. Till now, it is there. There is a lot many revolution happened. But I'm not going to cover this on the J1N39. We are focusing on the CAN. This is an extension for the CAN. Let's jump for the CAN FD in the next slide. So nowadays, most of the automotive industry are started working on the CAN FD. They wanted to use this FD CAN FD protocol. FD means flexible data rate, and the beauty of this data is extended CAN is basically flexible data rate CAN is data field size. If you see earlier, we were able to send only 8 bytes of information in a single frame, but here you can send 64 of bytes of information in a single frame. That's the beauty of this CAN FD. So it is a serial communication protocol which efficiently supports a distributed real-time control with very high level of security. Data byte maximum size is 64 byte, and it operates in the different modes: integrating mode, idle mode, receiver mode, transmitter mode, and very important that the baud rate. Earlier we have seen the baud rate maximum baud rate for up to the 1 Mbps only for even for the J1N39 and for the CAN standard CAN extended CAN frame, that is the CAN 2A to B, it's up to the 1 Mbps. But here you can send 12 Mbps. So CAN FD implementation happens on the controller host interfaces, new configuration registers, and interfaces directly to the physical layer, transceiver, transmit, and receive. So this is what the CAN FD is. Nowadays, most of the European automotive organizations started using the Ethernet as well. So the beauty of the Ethernet is the robustness as well as the baud rate. The baud rate is very higher compared to the CAN, but CAN is very trusted in terms of the error handling, prioritization, latency time, everything. That's what the evolution is going on. Most of the industries are started migrating and started working using the CAN FD protocol, and this is the future. I would say current as well as the future for the CAN protocol. I guess I have covered everything. If you have any specific question, feel free to comment, reach out to me, put down your comment into comment section. And thanks for watching this video. I hope after watching this video, or going through this training model, you will understand the basics of the CAN. Thank you. And please share, like, and subscribe my channel. Thank you.